For part 2 of your chapter 30 lectures, we're going to talk about Ampere's law. So Ampere's law is again a closed path integral. So we're going to look at the magnetic field dotted, so this is a dot product, with a closed path. And we expect to get some information about the current that we've enclosed. So when we talk about a dot product, we are saying we care about the portion of the magnetic field that is parallel to our path. And we're going to look at little increments of our path that we call DL. So here on the right-hand side of the screen, you have an image with a closed path, right? So this path happens to be a circle because that's what makes sense symmetrically around this current. So if we look at little bits of this path, we're going to call them DL. We're going to go around that whole circle. So this integral that we're looking at is actually that circumference of that circle. So from 0 to 2 pi a, since a is our radial distance there. And that should tell us something about the current that we've enclosed. So what we're really looking at is this area that's enclosed by the path there. So I'm going to use my highlighter. We're looking at this area that's enclosed by that path and looking at the current that punctures through that area, which you can see in the image right there. So the trick to using Ampere's law is to choose lengths so that our magnetic field that's parallel to those lengths is a constant. So if that magnetic field is a constant, we can turn this dot product into simple multiplication and we can pull that constant out of the integral. That's where it really gets useful. So we need symmetry for Ampere's law to be super useful. So if we look again at this image of a long straight wire and we choose a circular path, we have enclosed this current I. So instead of writing I enclosed, I'll just write I. And we're going to do an integral that looks like B dotted with DL along this path. So we've chosen a path so that B dotted with DL is just B times DL, and we've chosen a path that's the same radial distance away so that we expect our magnitude of our magnetic field to be a constant at that constant distance away from the wire. So now this closed path is just saying what is the path we've gone along. So in integral of all these DLs, you're adding up all these little bits of length. We fully expect to get the circumference of that circle that was our path. So 2 pi times a, because a is our radius in this case. So if I move things around, I get something that looks like this. I get a mu0 times I divided by 2 pi over a, which is our radial distance away. And that is the strength of our magnetic field. So that is the same thing that was found experimentally. And so maybe now you see why mu0 has a pi in it, and we also have that separate 2 pi outside of it. It's from Ampere's law. So this is the same result as we had before. So we can say that the magnitude of the magnetic field from a long straight wire, both by Ampere's law and by observation, is mu0 over 2 pi times the current divided by the radial distance away. Now, if we want to figure out direction, we're going to get the direction from our right-hand rule, just as what is visualized right here. All right. So Ampere's law is really useful when you can claim that your current is steady and continuous. We're going to make some modifications to Ampere's law to deal with things like capacitors, where it is not steady and continuous. All right, so when we have no current present in a wire, we've got all our compass needles pointed in the same direction. So that is not a steady and continuous current. We have zero current enclosed. Ampere's law tells us that the magnetic field there is zero. When the wire carries a strong current, we see a steady change in our compass needles, right? And so we can measure the magnetic field, and we get from Ampere's law that result that I wrote on the previous page, that we have some constants times I divided by R, right? And you can even visualize this. This is using some iron filings that align themselves in the direction of the magnetic field. So you can even use that to help you visualize the magnetic field around a current carrying wire. So let's do an example where we would use Ampere's law. So we're going to look at the field inside and outside of a wire. So we've got a long, straight, cylindrical conductor that's got a radius, capital R. It carries a current that we'll call capital I of uniform current density inside the conductor. We want to determine the magnetic field, both inside and outside this conductor. So I'm actually going to start with the easier case. Let's start with the case where we're looking outside the conductor. So outside the conductor, if I use Ampere's law, I am going to use a B dot dl. Tells me something about the current enclosed. And I'm going to use this Amperian loop is what it's called. So this path that's labeled number 1 here. So this path that we've labeled number 1, the I enclosed just happens to be the total current I that is described in our problem statement. So for our radius greater than the radius of our wire, so outside our wire, we're going to do one of these that's going to look like the result that we had before. So we've got 2 pi r, we've got mu 0 I. And so we've got that the magnitude of our magnetic field looks like mu 0 over 2 pi I over r. And again, this is when we are outside the wire, right? And the direction we're going to get from the right-hand rule, I'm going to call it phi hat, right? So I'm going to call this direction phi hat if this direction is z hat, and this direction is r hat, or sometimes s hat is used in cylindrical. Okay, so that's not too surprising. The stretch in this example is the region where we are inside the wire. Right, so that's going to be described by this Amperian loop number 2. So when we are inside the wire, we're going to start again with our generic Ampere's law, which tells us that our magnetic field dotted with the path we've gone around, we're going to take a closed loop integral, and we're going to say that is related to mu 0 and the current we've enclosed. Well, here we haven't enclosed the whole wire, so we haven't enclosed I. What have we enclosed? So here the I enclosed is just a fraction. So remember it said our current density, so our current along the wire was uniform. That lets us say this, that our whole current is this current I that is along the entire cross-sectional area, pi capital R squared, of our wire. But we're only enclosing a fraction of that. We're only enclosing this pi lowercase r squared of that wires, of that current. So we can only count that much as our I enclosed along this path. So again, we're going to claim that we can turn our dot product into simple multiplication, and we're looking at a uniform magnetic field at that uniform distance, and that our I enclosed is this fraction of the total current in the wire. And again, that reasoning comes from that phrase that the current density is uniform. So that lets me know that my magnetic field is mu 0 divided by 2 pi r, right? And this is something I can simplify a little bit more, right? That it is going to be some pi's cancel out, some r's cancel out, so that my magnetic field looks like mu 0 over 2 pi capital R squared I times R. And again, we can use our right-hand rule and get that our direction is in that same phi hat direction per our right-hand rule. Right, so that's kind of interesting. We could even graph that, right? So if we look at our equations here where we're inside the wire, mu 0 I 2 pi r squared are all constants, and then r is the thing that's changing. So our magnetic field is proportional to r. Here outside the wire, we came up with the equation mu 0 over 2 pi I, those are all constants, and then over r. So our B is proportional to 1 over r, right? So we can see that the maximum magnetic field is right here at the surface of the wire. All right, next time we'll pick up with magnetic field of the solenoid. This is a good place to pause.